session we are going to talk about top down design methodology in mixed signal current mode control. So, in this lecture we will first talk about digital current mode control and its mixed signal implementation and what is the top down design methodology in digital current mode control. So, we have discussed about the mixed signal current mode control architecture. This is one of the architecture of digital current mode control, and this we have discussed in sufficient detail in week 2 as well as week 3 in the MATLAB simulation. So, in this architecture we have the current loop in analog, and that is the sense inductor current, that is what we call as a V sense, and then we also have the feedback voltage loop which is in digital, and we need a AD converter for voltage sampling, and this you are sampling the feedback voltage where there is a resistive divider, and then this is coming inside the controller, because before we go detail about the FPGA. So, here we will be using an FPGA device for implementing this digital control, and the FPGA device will take the digital data from ADC, and this N out is the digital number corresponding to the output voltage, feedback voltage, that means the analog signal. Then we have a reference command, then error voltage, then it goes to the compensator, and we are talking about a digital PI controller for current mode control, digital PI controller. Then the control output again is a number. Then there is a current reference generation which ensure that we should first of all, whatever the control output, the data format has to be consistent with the DAC input data format. So, that means that is for the compatibility issue, compatibility purpose we are using this block, and also we are putting a peak current limit. So, all this block will be taken care by this current reference block. Then again we have a PWM and the dead time block. Okay. So, if we take the realistic implementation of the mixed signal current mode control, this is a feedback gain, and we have discussed in the previous lecture when we are talking about digital voltage mode control, because there is a resistive divider and this is coming as a feedback gain. So, feedback gain here is R2 by R1 plus R2 for this resistive divider, and it is approximately coming to be 0.27 for this case. So, this is 0.27 approximately our calculated value. Now, this data which is coming inside the controller we are calling as an ADC data that we have discussed. That means, we have, let us say, the feedback voltage which is voltage feedback, we have ADC, and this ADC we are getting ADC data, and this ADC is sampled using ADC clock, and this ADC clock we are using 25 megahertz clock. And we have discussed in detail in the digital voltage mode control that when you are sending 25 megahertz clock, that means the TADC will be 40 nanosecond. That means, and it takes about, so what is the sampling delay? The sampling delay here is the 40 nanosecond into 6 unit that we have shown, right, nanosecond. So, it is roughly around 240 nanosecond. This is simply because of sampling, because this is a pipeline ADC where there is a 6 cycle delay, and we are using a high frequency clock so that we can reduce the overall conversion time. So, in pipeline ADC the conversion time depend on the number of cycle, and when it comes inside the digital platform we are using a clock which is our switching frequency clock. This is a register. So, this clock is like, this is our switching frequency clock. So, this register is updated and this data we are getting in out. So, this is here, and here we are talking about in Q1.9 format. It is a signed number 1.9 format. Okay. Now, after that the reference signal has to be, and it has to be scaled according to this, and we are talking about again Q1.9. This is Q1.9, this is also Q1.9. Okay. Now, this controller, when you go inside the digital controller, we have a separate lecture for that. We will discuss about what is the format, sizing, what is the requirement. So, we are using, so we will talk about this bit size in detail. So, let us first understand the overall thing. So, this is the digital part, then the current difference, it is in digital, then we are giving a digital data to the DAC, and DAC is generating the analog voltage, and that is directly compared. Now, there is a current sensor, because you are using current sense resistors followed by a current sense amplifier, and this Kc is coming to be around 10 into 10 to the power milli. Since it is converting current to voltage, so it will be volt per ampere, right, because output is ultimately a voltage Kc, because Vsn is what? Vsn is basically Kc into IL. Okay. Next, this current mode. So, we understood that this part is analog world, analog voltage. Again, this voltage is in analog. So, this is digital. So, naturally for this interface we need an ADC, for this block we need a DAC. Okay. So, after this there is an analog comparator. So, this is our analog comparator. Output of the comparator goes to a latch circuit. So, this again is the digital block and the dead time circuit. So, we have discussed about the dead time circuit in lecture number 70. So, this is the block that we are going to discuss. So, in the FPGA we want to implement this block that we have discussed. What is this? So, we have discussed that we have a feedback voltage and there is an ADC. ADC require a clock, and this is we are sending like 25 megahertz clock, 10 bit data, it is Q1.9 format. Okay. Q-tran is the type of transient, whether you want to use load transient or the reference transient, that we have discussed. If Q-tran to be, that means what we are considering, if Q-tran is 0, then we are talking about load tran. If it is 1, then we are talking about reference transient. F clock is a switching frequency clock, and this is 100 megahertz clock. Q comparator is the output of the analog comparator. So, it is also coming inside because it is a digital number, it is on off pulse. Then output of this mixed signal, because we have a DAC. So, DAC data, this is coming to be an offset binary. And it is 12 bit data, and the DAC voltage, the span of this span, I would say the output range, instead of span I would say range. So, the range, analog range that we are considering with the driver, including the driver, because there will be DAC plus there is a driver also there, DAC driver. So, it is coming from plus 1 minus 1 volt to plus 1 volt. So, this is a range that we have. And this gain is what? It is like a 10 into 10 to the power minus 3 volt per ampere. So, that means if we set a maximum of 1 volt, which corresponds to, that means for Vp max to be 1 volt, this implies if you set the actual current limit max will be 100 ampere, because this is there and this is not acceptable. So, that means we need to set this value accordingly, which we want to limit to 10 ampere or less than that. So, we want the current limit to be less than 10 ampere, that is our requirement. So, we need to accordingly define in terms of the current difference. Then another output is the DAC clock that is coming out of the controller FPGA, and again it is 25 megahertz clock, and DAC data is a 12 bit data we have discussed, this is 10 bit data. Then we have PWM high signal, PWM low signal, and this goes to the load. What is the load? If you take the buck converter, this capacitor, so we have a continuous load, I will say R continuous, and there is a switching load. this is like RSW load, and this is our QL. So, if QL is 0, the switch is off. If the QL is on, the switch is on. If the switch is on, these two resistance will come in parallel. So, the effective resistance will be smaller. So, it will make a load step up transient. So, in this particular design, we have multiple modules. The one module is the main module. So, this is a main module which will mix the digital current mode control. Inside that module, we will have a sub module, clock generator, digital PI controller, current reference and the current limit that block, and PWM and the dead time, because we are talking about fixed frequency control, and here we are talking about trailing edge modulation. We have discussed trailing edge PWM, okay, and there is a dead time circuit. So, we are like around 50 nanosecond or 60 nanosecond, we are setting the dead time. Now, the main module, if we go, the main module will, that means it is consisting of, this is the main module. So, main module name may be MixedSignal underscore current mode control. What are the input to the main module? Main module, if I say main module, because we will discuss about the Verilog code next, but before going that in this lecture, main module, what are the input to this we need to give? So, we need to provide the module name that we will discuss. Then we have input data. So, what are the input? ADC data is input, Q turn. So, this is a vector input. Then these are all scalar input. Okay. Then this is the vector output. This is a scalar output. This is also scalar output, and these are all scalar output. Okay. So, we need to create the main module. Now, the clock generation block, we will discuss about this. So, what does it do? It takes the highest frequency clock. So, its job is to take the high frequency clock, then clock division, and it is going to generate one for switching frequency clock. So, this is like a 100 megahertz clock, and here we need 200 kilohertz. Then we are using FADC, which we are taking here 25 megahertz, and there is one more FDAC. This is also 25 megahertz. That means, what is the division ratio we need? This will be 1:500 division. This will be 1:4 for both the cases. Okay, so, clock division. Then we need a digital PI controller. So, here we are using a digital PI controller, and we have discussed about this structure earlier. How does the digital PI controller look like? Then we also need a current reference generator. What is the job of this? The format of NP and the format of NCON is different. First of all, there will be size. So, we need to resize it. We know about the Q format. This data is offset binary. This data is 2s complement. So, that means we need a codifier which will convert one code to other code, including the resizing of the data. Okay. And here we can also set the current limit. Okay. Next, the PWM and dead circuit. So, this part will be PWM, trailing edge modulator with dead time, and we will be discussing this. So, in summary, we have discussed digital current mode control and mixed signal implementation, and we have also discussed the top down design methodology in digital current mode control, and we will be discussing in the continuation of the next lecture more detail about the implementation as well as the Verilog codes. That is it for today. Thank you very much.